All right, let's first begin by reviewing parallel perpendicular lines. Actually, let's go over the three forms of lines. First form is called the point slope form. It's called a point slope form because it has one point and a slope in it. And here it is. So if I give you a point and a slope, and I ask you to put it in point slope form, all you have to do is enter these three numbers and you're finished. The second form was a slope intercept form. The slope is m. The intercept is actually the actual y-intercept, and that's represented by the letter b. And there's that form. 90% of the time when you're asked to find the equation of a line, that's the form they'll want it in. Because from this form, we can graph it. Remember how we graph this one? Plot the y-intercept, then follow the slope from that point. Third is the standard form, where A, B, and C are numbers, real numbers. When we say real numbers, we mean real numbers. What do I mean by real numbers? Okay, we'll do that next. Because there are two types of numbers, imaginary and real. So we'll go over that in a second. Standard form equations look like this. The x and y are on the same side. And then just the numbers on the other side. Only stipulation is A has to be positive. If A is negative, change the signs across the entire equation, both sides. And there you have it. All of these equations started from this equation. Right, so right here, if I take this equation and I multiply both sides by the denominator, I get this one. Y2 minus Y1, M times X2 minus X1. And then once I'm here, once I'm given a point and a slope, then I solve for Y. I get this one. Then from here, I move X and Y to one side and I get, so they're all related to each other by simply moving around. All right, so those are the forms of lines that we're talking about. If you have two linear equations, there are four possibilities. What does a linear equation look like? Let me review that again. What does a linear equation look like? That's a form of an equation. But how do you know if you're looking at something, even if it's in standard form, how do you know if it's a linear equation? No, all functions can be graphed. Remember when we did the library of functions? Oh, you guys are supposed to have a practice of pop quiz this morning on that. A linear equation, as opposed to all the other functions. Linear equations do not have exponents or any special operators. Again, by special operators, I mean square root, absolute value, anything. Here we have three examples of equations. We know they're equations because they have an equal sign. Is the first one linear? ¿Por qué no? Because it has an exponent. This is a quadratic equation. And that's in the library of functions. Is this one linear? Because nowhere in the equation are there any exponents or special operations. How about the third one? No, this one's squared. So this one is actually called a hyperbola or hyperbolic equation. This equation looks like this because the y is squared. This equation, since it's quadratic, x is squared, looks like this. This one's linear, it looks like that. Again, memorize the library of functions. Because next class, we're going to talk about, if I give you any type of function, you can be able to look at it and tell me what the graph looks like. The shape, the direction, everything, just by looking at the equation, doing no math whatsoever. So that's very important. And we'll also need it in the next chapter. We'll come back to this in a second. But we talk about real numbers. Real numbers begin with the natural numbers. What are natural numbers? If I ask you to count to 10, where do you start from? That's what these are. These are also called the counting numbers. So this is 1, 2, 3, 4, all the way to infinity. This leads to whole numbers. The whole numbers begin with a whole. And then they go on from there. So this one now has a 0. That leads us to integers. Those include the negatives, from negative infinity to positive infinity. No decimals, though. The rational numbers. These are your fractions. Because in the integers, we're going from negative infinity to positive infinity, but we don't talk about any decimals. This one goes from negative infinity to positive infinity, including decimals. So those are your real numbers. Any number you can think of. And inside this list, there are numbers like pi, which is 3.1418. There's a number called E, called Euler's number, 2.17181715. But there's some constant, but these are all decimals. And then we go on to the other side of the screen, which is called imaginary numbers. By definition, again, mathematicians are not too creative. You know the definition of imaginary numbers? Not real numbers. The reason they came up with these is because in engineering and sciences, you get with an equation, you could work it out. And eventually you get to a place where you'll get something like this. Square root of -4. You cannot have that because a square root works what number times itself equals what's inside there. So what number times itself equals -4? No, negative times negative is a positive. Positive times positive is positive. So this doesn't exist, but it comes up. So that's when they call this imaginary, I. Whenever you have something like a negative inside a square root, it's an I. So this answer would be 2I. Because 2 times 2 is 4, and that negative becomes I. So then the real plus the imaginary equal something we call complex numbers. And they're written like this. A plus BI, where A is a real number, B is a real number, but it has an I after it. So this is an imaginary number. So it has real plus imaginary. And you know what? You guys have learned this before. In 5th or 6th grade. But again, you never talk about it since then, so you forget about it. So these are the entire number scheme, the scheme that we have. Okay, so let's look at some. Whenever I say imaginary, or if I look at whole numbers, or integers, or rationals, you know what we're looking at now. Let's get back to look at if we have 2 lines, there are 4 possibilities. The 2 lines can look like this. This is line 1, and this is line 2. These lines are called parallel. They have no solution. These are lines that go on infinitely both ways. Here I have a second line. These are two lines here. They're the same line. This one has an infinite number of solutions. Every point on this line is a solution. So what does solution mean? When we have two lines, what does solution mean? Yes. So here we're talking about a solution. The point or points where the two lines intersect, where they cross. So how do we tell these two lines? Since if we have two lines, how do we tell these two apart? What do they both have in common? Very good. The slope of line 1 equals the slope of line 2. They're both the same slope. And here's an X and Y line. Here's an X and Y. Likewise, this one. So if your two equations have the same slopes, they're either parallel. Well, a shortcut to abbreviate this, we just write those two little hash marks. If the same slope, then they could be the same line or they could be parallel. What makes them different? The y-intercepts. Because parallel lines, the y-intercepts have to be different. If they're the same y-intercepts and the same slope, then they're the same line. Another one. Now they intersect. But if they have a 90-degree angle, they form a right angle. We call these perpendicular lines. And their shortcut is simply the upside down T. This one, since they intersect at one point, they have one solution. That's the solution. So this is line 1. This is line 2. This is line 1. This is line 2. The last one is any other pair of lines. They're going to have one solution. But there has to be a way we can distinguish their differences. Obviously, their slopes are different. But perpendicular, the slopes are negative reciprocals of each other. To find perpendicular lines, change the sign and flip the slope. To find perpendicular, change the sign, flip the slope. And at the end of class last time, I gave you these examples. Here we have four possibilities, or examples. If the slope is 3, what's the slope parallel? 3. Because parallel means same. What's perpendicular? What does 3 look like? Every number can be written as a fraction. So 3 is 3 over 1. Remember, what do you do for perpendicular? Change sign and flip. So if I change the sign, what's this one going to be? Positive or negative? It'll be negative because that one's positive. This is 3 over 1, so this one's going to be, that's all there is to it. If the slope is negative 2 over 5, parallel is going to be negative 2 over 5. Perpendicular is going to be, let's change the sign so it's positive. Flip the slope. These two are where a lot of people mess up. A 0 slope looks like what? Horizontal, exactly. This is a horizontal line. It looks like this. If we have our graph, it's a horizontal line. So the fraction of this, how do you make it into a fraction? 0 over 1. Anytime the top number is 0 over fraction, it equals 0. So the parallel line is the same, so it's 0. What's the perpendicular? 0 doesn't have a sign because that's neither negative or positive. So you flip it. This one becomes 1 over 0. Which is undefined. One over 0. Whenever you see if it's undefined, we have 1 over 0. So that's what this one is. Undefined means that we have 1 over 0. So the parallel line has what slope? 1 over 0, if it's parallel. It means we have it undefined. If it's perpendicular to the undefined line, we have 0 over 1, which is 0. Now, the reason these cause problems is how many times does 1 go into 0? 0. It can't go in there any times. But how many times can 0 go into 1? Infinitely many. I could give you nothing forever. That's why it's undefined. There's no number that can define how many times 0 can go inside 1. That's why instead of putting infinity, we put undefined. Tell me if these two lines are parallel, perpendicular, or neither. Let's work this one out together. Because I didn't tell you the steps yet. Here are the steps. This is the steps to determine parallel or perpendicular. First step. Set both equations to y equals mx plus b. Why do we do that? Yeah, because remember our chart of our four possibilities? The way we compare them is looking at the slopes and the y-intercepts. Then you compare the slopes and y-intercepts. That's all there is to it. So this one's already done. Line 2 is -4/3 x minus 2. So the slope is what on that line? Yes. The slope is whatever number is in front of the x, positive and negative. It doesn't matter which one. So it's -4/3. The y-intercept is, it's whatever's by itself, -2. Remember, the signs belong to the numbers. So we have to take this equation and do what with it? Yeah, we have to solve for y. So we subtract 4x from both sides. We got -3y equals -4x plus 6. Since that's a negative in front of there, next step is change all the signs. That becomes +3y, +4x minus 6. And then last step to get y by itself, we divide each term by 3. 4/3 x, 6 divided by 3 is 2. So what's the slope of this one? And what's b? So how are these two lines related? Are they parallel, perpendicular, the same, or neither? Uh-oh, we have a smackdown. We have people saying different things. Who thinks they're parallel? Who thinks they're perpendicular? Who thinks they're the same? Who thinks they're neither? No. Look at the slope. What's the slope? This one goes down. What's the slope? Yeah. So again, it's the negative signs are going to hurt. So this one's going down, this one's going up. The only thing they have in common is the y-intercept. That's what come on these right here. We don't talk about the y-intercept because they can meet, they can cross at the y-intercept. If the slopes are different, then they're going to be one of these two. If the slopes are the same, they're going to be one of these two. So the slopes are different. We know they can't be parallel or same. They have to be one of these. Let's do another one. So we have to solve for y. So we have to get rid of first on this side. We're solving for y. Well, get rid of the 3. So we subtract 3 from both sides. We have negative 4x minus 3 equals positive 2y. We can rewrite this as 2y equals negative 4x minus 3. Just flip them over. Get the y by itself. Since they're multiplied, we divide each term. Only one negative, so the answer is negative. 4 divided by 2 is 2. So there's this one. The slope is negative 2. The y-intercept is, what's the location of the y-intercept? Location. I want the coordinates. Because the y-intercept is negative 3 over 2, but the location is 0, negative 3 over 2. Location is a point. So you're going to be asked those kind of questions online. Is what's the location, or what is the intercept? What is the location of the intercept? So 2 different questions. Other one. Well, we know it's already solved for y, so m is equal to negative 2. The y-intercept is 1. So what do we notice about the 2 lines? Well, yeah, they have the same slope. So they're the same lines are parallel, but they have different y-intercepts. So M1 equals M2. B1 does not equal B2. So parallel. That's all there is to it. Find the solution, if it exists. Is it going to have a solution? Two lines will have a solution if what is true? A solution, a single solution. Two lines will have a solution if what is true? This would be a good time to go back to this picture. Two lines will have a solution if what is true? Exactly. They will have one solution if the slopes are different. So if you're looking for a solution, first off, make sure the slopes are different. Or they're the same line. If they have the same line, all points are solutions. So the slope of this one is 3. The slope of this one is -2. So we can go ahead and go. If the slopes were the same, what can we conclude? Which, or, yeah, if the slopes are the same, they're either going to have no solutions. You're going to have no solution, or they're going to have infinite solutions, all depending on what the y-intercepts are. So the slopes tell us a lot. If the slopes are different, we're guaranteed one solution. If slope 1 does not equal slope 2, even if it's perpendicular, the slopes are going to be different. So here are your steps. Put into y equals mx plus b. So we have y equals mx plus b. Set both equations equal to each other. Why would I do that? We solve for y. We solve for y. Why would I set them equal to each other? Well, yeah, but what is the reasoning I'm doing that? Well, yeah, if we have two lines and they intersect at one place, that means the x's have to be the same and the y's have to be the same at that point. So that means the y of line 1 has to equal to line of y2. They have to have the same point if it has a solution. So we have y1 equals y2. So it's -2x plus 1 equals 3x minus 5. Solve for x. Okay, here we have another mini lecture. We're trying to get x by itself, right? We have x's on both sides. Which one do we move? Yes, which one's smaller? The -2 is smaller than 3. Always move the smaller x to the larger x. The reason we do that is so we have a positive coefficient. If we move the 3 over here, we'd have a -5. We have to worry about the negative. But if we move the 2x to the other side, we don't have to worry about the signs. 3x plus 2x is 5x. Get the x by itself, but we now have to get rid of 5. So we have to add 5 to both sides. 6 equals 5x. Next step. Divide both sides by 5 because we want to get the x by itself. So there's my X value. That's the X they both share together. So now plug X into either equation and solve for Y. Because if they have a solution, the point where they meet have to be the same in both lines. So which equation is going to be easiest to put into? The first or the second? You'll get the same answer. It doesn't matter which one you put into, but you get the same answer. So which one would be easier to put it into with less worries? We know we have our two lines. And we know X is equal to 6/5. Which line are you going to put it into? First one or the second one? And why? Why? It's got a negative. Negatives are never easier. Because you have to worry about the negative. Whenever you have positive numbers as coefficients, it's always easier because you don't have to worry about any sign changes. But let's go ahead and, since you all chose that, let's go ahead and do that. So we plug in place of X, we put 6/5. If you don't like dealing with fractions, remember we found a way around it. Get rid of the fractions. Can we combine these two? Yeah, this is 2/1. What's the rule for multiplying fractions? Reduce if possible. Can anything cancel top and bottom? No. 2 can't cancel the 5. 6 can't cancel the 5. So multiply numerator times numerator, denominator times denominator. So negative times positive is negative. 2 times 6 is 12. 1 times 5 is 5. But okay, from this point here, there are two ways you can, actually, there are three ways you can solve fractions when you're adding fractions. And I'll show you all three ways. First way, in order to add and subtract fractions, you have to have a common denominator. So what is 1? The common denominator is going to be 5. What is 1 equal to with the denominator of 5? Once you get a common denominator, you just have to worry about the top now. The negative 12 plus 5. And this is the reason why the top number is always positive or negative. Bottom number is never negative. Because whenever you get a common denominator, it's always going to be positive. The sign changes only on top. Negative and positive, 12 is bigger, so it's negative. 12 minus 5 is 7. So it's negative 7 over 5. Another way you can add fractions is the butterfly method. Multiply the diagonals. 1 times negative 12 is negative 12. 5 times 1 is 5. And you add them. So negative 12 plus 5 is negative 7. On the bottom, just multiply. 5 times 1 is 5. Or we can get rid of the fractions. The LCD, the least common denominator is 5. Multiply each term by 5. So you find the LCD, multiply each term by the LCD, reduce. So the 5s cancel. Multiply, get rid of the parentheses, which we did. Combine like terms. Negative 12 plus 5 is negative 7. And solve for y. Divide both sides by 5. Is there one good way as opposed to another? No, not really. They're all the same. But whenever you have fractions and equal sign, this is the one I'd use, because learn one method and stick with it. It'll always work. If you learn multiple methods, then you can get mixed up. Solutions of functions, we call those zeros. So the word solution is synonymous with zeros, which is also synonymous with the x-intercept. So how do you find the x-intercept? Set y equal to 0. That's why it's called a zero. The 0 says, at what point, what x makes y equal 0? That's what it's looking for. What x makes y equal 0? That's what we're looking for here. Whenever we talk about solutions or zeros or intercepts, that's what we're looking for. So set y equal to 0. Solve for x, and that's your solution. So that's your solution. And that's the stuff we've been doing all along. So if you have any equation, just set y equal to 0 and just solve for x. And there's your solution. Okay, let's finish up the chapter by doing that worksheet I gave you. Inequalities. I have to give you a heads up first. We have certain notations. Parentheses represent something that's not included. Likewise, an open circle means that number is not included. And likewise, the inequality symbols. Less than, greater than. Why is this one less than? Why is this one greater than? Because we read left to right. This number is smaller than this number. This number is bigger than this number. It always points to the smaller number. And the second one, brackets represents the numbers at the end are included. So is a solid dot, or if it has an equality symbol. This is less than or equal to. Greater than or equal to. For example, on a graph, what this one says, if I ask you to list the numbers, in this one, you would give me 4, 5, and 6. That would be my answer, my solution set. Because this parenthesis says I cannot use 3. It's not included. The bracket, however, on the other hand, is 6 is included. This means the same thing. This one says all the numbers larger than 3, but not equal to 3, and less than equal to 6. So this is 3 is less than x is less than or equal to 6. So that's what we're going to look at right now for the next 15 minutes of these different variations. All right. Let's begin. We have 3 different types of notations. Set notations deal with the inequalities. Interval notation deals with the brackets and parentheses. And graphing deals with the dots and open dots. Infinite and closed. What that one means is this. It goes on, I'm reading left to right, so it's going to negative infinity and it's closed at some number B. So what would that look like? It says that X is less than or equal to B. Let me see if there's any more here. I'll give you the sheet when I'm finished. Yeah, I'll give you the sheet when I'm finished. All right, and that's what that says. I'm reading left, right. So this is anything. Here's B. X is anything less than. An interval notation. When you fill these out, start from the left side and go to the right. On the left-hand side, we start with negative infinity. That's where we start. And when do we stop? At B. Parentheses means I cannot. Can you ever get to negative infinity? No, it's impossible. You can never get to it. That's why infinity and negative infinity are always parentheses. But since we can use B, it's a solid dot, we put a bracket. Likewise, this one. We started at B. We're going this way now. So remember, this is the X line. All of my X's are greater than or equal to B. Why is it equal to B? Because it's a solid dot. If it's solid, that means I have an equality. What's this one going to look like? What do I start on this one? I start at B, and I go to positive infinity. I'm going to the right. Infinity is always a parenthesis. Can I use B? Yes. So it's a bracket. Let's look at that. What does my X tell me my numbers are? Well, my set notation, my X values are going to be strictly less than B because it cannot equal B. Since it's an open circle, I cannot include B, so it's no equal sign. The interval notation is my interval begins at negative infinity and ends at B. Open always on, but since I cannot use B, it's an open circle, I use a parenthesis. Likewise in this one. X is going to be strictly greater than B. Look at these first four. Well, let's do this one here. So I start off at B and I go to positive infinity, but I can't use the endpoints. As long as your X is on the left-hand side, on the set notation of these graphs, notice the direction of the arrow. It's pointing the direction of the shaded region. Since I begin at B, I'm going to the left. I begin at B, I'm going to the right. I begin at B, I'm going to the left. I'm going at B, going to the right. So as long as your X is on the left-hand side, whatever arrow is, the direction is pointing, that's the area you're going to shade. Okay, now we're going to get something called finite and closed. Finite means it has a beginning and an end. What this means is I'm now going to be between A and B. Reading left to right. What's my smallest? I can get to A. Can I use A? Yes, since it's a solid dot. That means all my x's are between there. Again, this represents where my x is and the endpoints, whether it has a line or not. I begin at A and go to B. That's my domain. And they're both used, so I use brackets. Finite and half open. So it means I have that area shaded. I begin at A. Here's my x's. I can use it so it's less than, A is less than all these x's and equal to, but it has to be strictly less than B. I cannot use B. So the interval notation, I begin at A and go to B. A is a dot, so it's a bracket. B is an open circle, it's a parenthesis. Pretty easy. I remember this from high school. You'd be surprised. A lot of people never learned this stuff. That's why I have to go through it. Finite half open. Again, I'm going between A and B. I cannot use A, but I can use B, so it's equals. So my data set is between A and B. That's an open circle, so it's a parenthesis. Closed, so it's a bracket. Again, X is between A and B. I can't use either of them, so there's no equal sign. I'm going from A to B, and they're both open circles. Now it gets a little bit complicated because now we're looking at infinite closed bidirectional. So I start at A and I'm going to negative infinity. Also, my answer can be here. So if I'm thinking of a number, it could be here or it can be here. In set notation, X can be less than or equal to A, or X can be greater than equal to B. That's what that says. Remember, these are my X's. The word or in interval notation, reading left to right, I start off at negative infinity. I go all the way to A. I can use it. I start at B and go all the way to positive infinity. Inside here, I use the union symbol, the U. That's the same thing as the word or. Bless you. I'm going both directions. So here, my X is going to be less than or equal to A, or it's going to be strictly greater than B. Negative infinity to A, it's a solid dot, so union, it's open, B to positive infinity. These are my X's. So X can be strictly less than A. I cannot use A. Or X can be greater than or equal to B. which is negative infinity all the way to A, union with bracket B to infinity. X is strictly less than A, or X is strictly greater than B. I cannot use A or B. They're both open. So it's negative infinity to A union with B to positive. I can't use the endpoints. Those are pretty easy. So how would you do those next two? How would you represent a point using set notation? Very good. X equals A. How about an interval notation? Can we use A? It's a solid circle, so we can use it. What symbol, parentheses or bracket, do we use for the solid dot? The solid dot means brackets. And the opposite, what this one says is all of this is my solution. In interval notation, it's pretty easy. It's just not A. This one, I could write this one two ways. I can either go from negative infinity to X is less than A, or X is greater than A. Or I can write X does not equal to A. They both mean the same thing. The last one, all real numbers. Remember, the all real numbers, the symbol for all real numbers is that R. In interval notation, negative infinity, positive infinity. We just put X. Or if you want to, you can also put negative infinity to positive infinity, but just X will work, because that means there's no restrictions. All right. Next time we'll do some examples, and then that'll be the end of chapter 1. And we'll start chapter 2 next time as well. Okay, everybody. Have a great, safe weekend.